So what do you do if you have two forces or two velocities or two accelerations or two of any type of vector quantity acting on a single object, and you'd like to find the total effect of those two vectors acting on that object? In this case, this is a special case where the vectors are perpendicular to each other. In fact, better yet, they're actually lined up with their x and y axes. So let's figure out how to add these two vectors together to get a total, in this case, force. I chose to use force as our example because it's easy to imagine that if we had an object, for example, we have object 1, and we have two forces applied to it, one force to the right and one force up, so the total force would be pulling this object someplace right and upward into quadrant 1 if we were to imagine the xy axis overlaid on this point. And so in this case, I picked a case where we'd have a solution in quadrant 1. The other case I'm going to choose, I have another object, object 2, being pulled to the left with a force, a very large force, and being pulled downward with a somewhat smaller force. And the overall force acting on this should be somewhat to the left and somewhat down, but more to the left than down. So we'd expect it somewhere into quadrant 3 is where this thing's going to be heading with that total force. By the way, just an aside note here, a total force, we have several names for this total force in physics. We could also call that total force, or the sum of the forces, the resultant force, the sum of the forces, the net force, sigma f, sigma being the Greek letter capital sigma, which I have drawn over here. So here's the process we'll follow. To make it easier on ourselves, I'm going to do what's called a translation. Whenever you're adding vectors, it's always legal to do a translation of your vectors as part of the process. That doesn't change the action on the object. And a translation just means we can slide this around on our board here without changing the length or direction of it. And for object 1, I'm going to just do the slide first, and I'm going to explain why I did it. So let me get object 1 out of the way. And so what I've done is I've moved the vertical force, F1y, over to the right. And the reason I did that is that what I want to do is I want to line up these vectors such that I have a starting point to an ending point, and I moved it over so this start picks up where it left off and brings me up to here. And so start to finish, or tail to head, tail to head. I can do the same thing down here. In this case, in the case 1, I moved the vertical vector. In case 2, just to show you it doesn't matter which vector I move, I'll actually move the horizontal vector. And so here's my vector. I'm going to leave this vector in place, my f2y, my y, I call this a y component of my vector. And so that's my start and finish in red, and I'm going to move down the blue vector, and let me get object 2 out of the way. And so once again, I have start to finish, start to finish. All right, that being done, where is my total? Well, as you recall, I predicted that the total for case 1 would be pointed somewhere into quadrant 1, and in case 2, somewhere into quadrant 3. So here's how you get the total. The total, which is the sum, starts from our original starting point, and it goes all the way over to our final finish point. Our original starting point over to our final ending point. So there's our force 1 from start to finish, and here's our force 2 from start to finish. So that's our total force. In purple, force 1, in purple, force 2. All right, how would we describe force 1 now? Well, force 1x and force 1y are easy to describe. Force 1x is pointed to the right, and if you look at my scale I chose here, I use 5 newtons per block. So I've got 5, 10, 15, 20, 25, 30. I've got 30 newtons to the right force pushing this, and 30 newtons upward force pushing this. On case 2, I've got 15 newtons downward and 15 newtons to the left. So I'm using left and right, up and down, and a value. In other words, I'm using a magnitude and a direction. Well, my question is, for these forces 1 and 2, what is the magnitude and the direction? How do I find that? Well, magnitude is just the length. How do we figure out the length of this? So this is a rectangular or Cartesian coordinate system that we're using. And because they're perpendicular, I have nice right triangles here. So what's my magnitude? It's the length of this, what do we call this? A hypotenuse. What's my direction? How can I describe direction? Well, what we typically will use is an angle. let's actually take a look at the magnitudes and the directions of these and figure out how big these new vectors are, or sums are. So to find the magnitude, all we're doing is taking our hypotenuse and finding the length of it using Pythagorean theorem. All right, I'm going to start on case 2. For case 2, I will use Pythagorean theorem. I'm going to take the square root of my one leg squared plus the other leg squared. I'll substitute in my numbers here. I've got negative 30 units, negative meaning it's going to the left, 30 newtons long. And my y value is downward, so it's negative 15 units. Remember, there's 5 units per block is my graph scale that I chose for this graph. So my total is, I'll just do the math here. The square root of 1125 is 33.5 newtons. Make sure that you do a little sanity check on the size of your number. Our two legs were negative 30 and negative 15. Our total, our hypotenuse, is the longest leg of a right triangle, so it should be somewhat larger. And if you just compare visually the length of these, yeah, the purple one's going to be somewhat larger than the blue, but not that much. And sure enough, here's my purple, our hypotenuse size. It's 33.5 is the magnitude. And our x component of our vector was only 30. So they're about the right ratio, I'd say. 33.5 is slightly larger than 30. So it looks like we're in the right ballpark and we didn't make a mistake. All right, let's actually figure out now how to do. So for our direction, I like to use direction for these situations relative to a horizontal line that the vector's up against. So our purple vector here, I would like to know the value of that angle right there. And we call this, in this case, an angle of depression. But this is the angle relative to horizontal, or relative to a level surface. Of course, we have alternate interior angles here, so that theta 2 is also inside of our triangle as our included angle right here. We use that as a reference angle. And how do we find this angle? Well, we can use SOHCAHTOA. And what do we know in this? We actually don't know the angle, but we know all three sides. We know this is negative 15 newtons for the y component. The x component is negative 30 newtons. And we figured out that the total is, our hypotenuse is 33.5 newtons. This is a rounded value for this hypotenuse, so I'd prefer that I use my more accurate measures, which are my two legs. And when I do that, you'll notice that at the opposite, over the adjacent, you'll recognize from trigonometry that our tan of our angle is our y value over x value. You've seen that on the unit circle before, so this is nothing new. If we use an angle that's relative to horizontal. We're not quite using a standard angle here, but you'll see later on there's a little advantage to using standard angles as well. Standard angles are always defined relative to the positive x-axis, which is relative to the horizontal direction. So I'll plug in some numbers here. So I'm going to solve for theta by taking the inverse tangent, or the arctan, of the ratio of the two sides. And I get inverse tan of negative 15 over negative 30, which is 26.6 degrees. So we've taken these two forces, F2y and F2x, and we've added them together to find out the total force acting on this object is in quadrant 3 as we expected. It's 33.5 newtons in magnitude, and its direction is 26.6 degrees. Now let's repeat that process for case 1. Well, there's no way I'm going to do that because this is a much easier problem. I'm going to recognize from geometry here that this is a special right triangle. This is actually half of a square. I've got a 30 unit long force pointing to the right and a 30 newton force pointed upward. So I've got two sides of a square, and this is the diagonal of the square. And how long is the diagonal of the square? Well, it's the square root of 2 times the side. And so we've got 30 square roots of 2 newtons. Of course, in math, we love square roots. In physics, just give me a number, rounded properly. So I calculated this to be about 42.4 newtons. So that's our magnitude, 42.4 newtons using special right triangles. Didn't have to go through all the math. How about the angle? Well, this is, what's another name for this special right triangle? This is a 45-45 right triangle. And so our angle, theta 1, this is relative to horizontal again. I'm going to pick, this is actually this is a standard angle from trigonometry and geometry, starting from the positive x-axis going counterclockwise. So this standard angle, theta 1, is 45 degrees. Didn't even have to do a calculation on that. As a reminder, what's the other special right triangle you should be familiar with? That's the 30-60-90 triangle, and and that is special because it is half of an equilateral triangle, and we know everything about an equilateral triangle to make those calculations. So that's how we add two perpendicular vectors. As I said, I chose two force vectors because it's easy to imagine a case where this could happen. But you saw in our 2D motion case, we actually had to add two velocity vectors again. But you'll see later on as well, we could add acceleration vectors or any other type of vector quantities. They just have to be the same type of vectors. They have to be the same type of physical quantity. Both force vectors, both velocity vectors, etc. And they all have to be acting on the same object for it to be a situation where you'd actually add.